So we've started with the derivation of the overall balance equations for your reactors or reacting systems, and we'll continue with that. Okay, so let us quickly recap what we did in the previous lecture. Okay, so we said that we can choose for any control volume, we can write balance equations. Okay, and this can be any arbitrary control volume. We choose a control volume such that it is convenient for our analysis, but you can literally choose any control volume and your analysis would still be fine, as long as you consider all the possibilities when it comes to things that are coming in, going out, appearing, disappearing, and so on, right. So this is a control volume, and we said rate of accumulation which is nothing but d by dt of extensive conserved extensive, it is an extensive variable and it is a variable that is conserved. Mass is conserved, energy is conserved, moles of a particular species are conserved, and momentum is conserved. Okay. So that is going to be equal to rate in plus rate of formation. Okay, and again we said from our sign convention, if something is being consumed, it's the value, the sign is just going to be negative, and that is going to take care of it. Okay, so we don't have to worry about whether the sign is correct or not, whether I should use plus minus. It's plus rate of formation, and your for reacting systems, for example, your stoichiometric coefficient will take care of the fact that whether it is being generated or whether it is being consumed. Okay. So then what we did was we talked about now things that are of interest to us is moles of all species, the overall mass, and energy. Okay, we then considered moles of all species in a well mixed reactor. So if we take a well mixed reactor, and let us just for convenience, let us just assume a liquid phase reactor. Okay. So this is, so there is one inlet, there is one outlet. Okay. Now let us say if this was gas liquid reactor, what will we do? We will basically do the balances for two different control volumes. Okay. One is we will do balance for this control volume, which is the liquid, and other is we will do balance for this control volume separately, which is the gas. Okay. And then in and out will be for the liquid phase and for the gas phase individually, and that is based on the control volume. So if for example there is dissolution of gas into the liquid, if there is something gas or a species dissolves into the liquid, it will be taken out from the gas phase, it will be added into liquid phase. Okay. This is something that we are going to do in module number 7. Okay. But just to give you a prelude, right now we are looking at single phase, but all of the analysis, all of the development that we are doing, there is no restriction of the number of phases, number of conditions and so on. We are trying to do more general analysis over here. Okay. It could very well be that the liquid phase is very well mixed, but the gas phase is not well mixed. That is perfectly fine. Okay. Then let us say we have a situation like this. Let us say there is liquid and there is gas, and this liquid is well mixed and the gas is flowing like this. Okay. We can always take a control volume in the gas phase. So, this can be the control volume in gas phase, and there might be multiple control volumes in the gas phase, and there might be one single control volume in the liquid phase. This can be one single control volume in liquid phase. Okay. You can very well do an analysis like this. Again, this is not something we are going to do right now, but just going ahead, what I am saying is that when you choose control volumes, okay, the choice is up to us, and the choice is based on the convenience for a particular problem. Okay. Okay. So, when we did this analysis for a well mixed reactor, d by dt moles of rate of formation of moles of K. Okay. So, this is going to be okay. So, this is how it would be. Again, when if it was multi-phase system, so let us say there was a possibility that species K can dissolve from the gas phase into the liquid phase, we will just have plus the source term, we will call it as one more source term or solubility term or dissolution term. Okay. If there was a possibility of something else evaporating or whatever from the liquid phase into the gas phase, that again will be captured by the same SK term. Okay. Something that we are not doing right now, so I will not add, but essentially looking forward, okay, the analysis that we are doing right now, the same analysis with fairly minor changes will be applicable at a later stage as well. Okay. So, most common cases in undergraduate that you saw was constant volume, batch reactor, or steady state CSTR. Okay. What does steady state CSTR mean? Things do not change with time. Okay. So, if it was a constant volume batch reactor, you do Fk in, Fk out are both 0, okay, and for constant volume batch reactor you got d by dt Vck equal to Rkv, and if constant volume then this comes out and if this comes out, you can cancel this and you will get Rk. Okay. So, if the reaction was if this was the case, then Rk or Ra was just going to be minus 1 multiplied by R, okay, and therefore, you will get or minus R, okay. So, that is the definition, that was what we used as a definition of rate of reaction. So, the IUPAC, and this is where the IUPAC definition came in. Okay. So, this is the genesis of IUPAC definition. So, the IUPAC definition is not really the definition of the rate of reaction, but IUPAC definition is a consequence of mass balance on a constant volume batch isothermal batch reactor. Okay. So, that is something that, for example, in your textbooks it is mentioned a couple of times. So, I just wanted to do that clarification. Okay. What if it is a steady state CSTR? Okay. Steady state CSTR, you also have to satisfy the mass balance. The mass balance is dm by dt or d rho v by dt is equal to mass in minus mass out, or d volume by dt is volumetric flow rate in minus volumetric flow rate out, right. And if V cannot change, then Q in has to be equal to Q out, okay, and that was what was used. So, overall balance okay. This is the balance for CSTR, okay. So, this is the overall balance, this is the balance that you might have used, this is the balance for a batch reactor that you might have used before, okay. But where does it come from? It comes from the overall balance that is given over here. Okay. This is where those cases come from. Any questions? Let us look at the other case. Okay. Okay. The inlet can be specified in multiple different ways. It can be specified in terms of molar flow rate, that is say mole per unit time. So, we will just use mole per minute, it could be moles per second, moles per hour. This is in terms of liters per minute or volume per unit time. This is nothing but centimeter per minute, let us say. or meters per second or whatever it might be. Okay, and Ck is in terms of moles per liter. Okay, again it's not really, I mean it need not always be liter, it can be moles per liter, it could be kilomoles per meter cube, which is same as moles per liter. It could be kilomoles per liter, it could be moles per cc, whatever it might be. Okay, you just have to be careful about the units. Okay, now we have discussed this plug flow reactor a few classes earlier, and the main assumption in a plug flow reactor is everything flows as a plug. Within the plug is fully mixed okay no interaction with adjacent plugs. Okay, so that was the idea of a plug flow reactor. Okay, so we can consider this location as Z, this location as Z plus delta Z. Okay, and we will consider flow direction to be this direction. If it flows in other direction, you are just, the sign would be negative, that is all. Okay, and what do you have is d by dt, and let us say the volume, let us say volume is A multiplied by delta Z, where A is the cross sectional area. Okay, d by dt of Ck multiplied by volume of the control volume, and the volume of the control volume is nothing but A delta Z, okay, equal to rate in Fk at Z minus rate out plus Rk multiplied by volume, and volume is A delta Z. Okay. Now, assuming that the area, I mean your reactor is a tubular reactor, it could very well be expanding reactor, in which case the next thing won't exactly be valid, but assuming that your area is constant, you can take A delta Z out and you will have equal to the right hand side. Okay, and this A delta Z you can divide throughout by A delta Z, and you will have okay, and if you take limit as delta Z tends to 0, you will get dCk by dt equal to negative dFk by AdZ plus Rk. Of course, your d's, these are not d's, but these are going to be partials. Okay, because we have taken the limit as Z tends to 0 holding t as constant. Okay, or we can rewrite this as Rk. Okay. In your undergraduate, you had looked at steady state. So, dou Ck by dou T was equal to 0, okay, and you had then used the expression dfk by dv equal to rk, okay. Q may not necessarily be constant. If it is liquid phase, your Q is constant. If it is gas phase, your Q would not be constant. Q might change if there is change in number of moles, okay, and that is what you had used in order to get this volume expansion coefficient epsilon and all that, okay. Continuing on to that, what we had done is design of CSTR, design of batch reactor and design of PFR, okay. So, what does design mean? Analysis basically means given a particular situation, okay. In analysis, the question that we are asking is given a particular situation, given that the reactor is a 10-meter long reactor, flow rate is so and so, inlet conditions are so and so and so on, okay. How does the reaction occur? How does the product form? How do side products form? How does selectivity change? How does yield change? So on and so forth with respect to time and or with respect to space, okay. The design problem instead is given that certain condition, which is conversion, selectivity, yield, etc. is desired, given that this is what we want from the system, okay. Given that we want certain yield, certain selectivity, certain conversion, whatever it might be, what is the volume or what is the flow rate or what is the time duration for operation of a batch reactor that will allow us to achieve that goal, okay. For a large part, you have looked at the design problems in your undergraduate, okay. So, let us look at again a CSTR. CSTR is 0 equal to Q multiplied by okay. The question you ask, oftentimes you ask is to achieve a desired conversion. And the desired conversion we defined as xk is nothing but fkn, okay. And if we take fkn over here, this guy you can replace this guy with this guy, okay. So this is essentially what you did when it came to design of a CSTR. Okay. Okay. So this is your familiar design equation. You wrote your design equation like this. Okay. In your undergrad, your design equation was written in this form. Essentially, this is what this guy is, right? Fkn xk plus rkv equal to 0. So 0 equal to okay. If we take this onto this side and divide by rk, we are going to get Ra, okay. And if our reaction was written in terms of A plus BAB given C by AC, if our reaction was written in this form, then our Ra is just minus 1 multiplied by R, okay. So we replace this by minus 1 multiplied by R, minus and minus goes away, okay. Or instead we can write it as nu A multiplied by R, okay. But we can expand our query to actually say what is the size of a CSTR or what is the operating condition of a CSTR, not necessarily to meet a certain conversion objective, but to meet certain selectivity objective or to meet a certain temperature objective or anything else, okay. That does not matter. What you need to look at is all of this was a consequence of what you did with the overall balance equation, okay. So this particular equation that we have over here, this equation has only one assumption, and that assumption is that the reactor is well mixed, okay. There is no real other assumption that has gone into this equation, okay. Everything else that you have done, okay, there is some or the other assumption that was made either beforehand or later on after the equation was derived. Likewise, when it comes to the PFR, other than the fact that it is plug flow, there is no other assumption that has gone into this, okay. Everything else that you have studied has some or the other assumption. In the definition of RK, we have not even assumed that there is 1 reaction, 10 reaction, million reaction. We have not said there is 1 species, 25 species, okay. The only thing that we have said, it is plug flow, okay. Now, if it were a batch reactor, what we had done in case of a batch reactor, okay, in case of a batch reactor you get dCk by dt equal to Rk, okay, actually not dCk by dt, what we get for a batch reactor is, okay, what we get is d by dt of Nk equal to Rkv. That is the batch reactor equation, that does not have any assumption, okay. Your design equation, so this is the batch reactor equation, that does not have any assumption, okay. Thereafter your design equation that you have used, okay, you do make certain assumptions that there is only one single reaction taking place. If you have multiple reactions taking place, you have to be a little bit more careful about this. If it is parallel reaction, no problem. If it is series reaction, you only look at the first reaction that A is taking part. If it is a network of reaction, you will not be able to use this equation, okay. So, in this course, rather than treating each and individual situation, for example, in your undergrad very likely first 2-3 weeks or first 3-4 weeks you would have done batch reactor, PFR, CSTR single reaction. Towards the middle of the course you would have done multiple reactions and look at selectivity and so on. Towards the end you might have done non-isothermal. Instead of that, we are going to consider all the cases under a more unified umbrella, okay. That is what we are going to do in a PG course, okay. Likewise, balance equation for plug flow reactor, this is the balance equation that we had earlier derived. Okay. Anything else, you know, comes with maybe with certain assumptions, okay. Steady state, first term goes out, okay, dfk by dv equal to rk, you get it because of steady state. If the reaction, if it was only a single reaction written in terms of A plus B by AB giving products, it was irreversible or reversible reaction, single reaction, you are going to get the equation d by dv fa equal to minus Ra, okay. This is where this came from, okay, okay. And thereafter this was your classic, this is called Levin-Spill diagrams. Okay, they came very simply by volume of a PFR. So, if you were to have 1 by minus Ra versus x, and if this was your target conversion, this guy is nothing but an area under this curve, okay. Whereas, if it is a CSTR, okay, it is nothing but product of these two, okay. So, if it is a CSTR, it is nothing but this guy and this guy, product of them, okay, which would be nothing but this particular box, okay. And then if you had to do two CSTRs in series, and first one has an x1 target and the second one has an x2 target, this one is x1, this one is x2, and then two CSTRs will be like this. If there were infinite number of CSTRs, it is just going to be integral under the curve, and that is where this idea of your infinite number of CSTRs is equal to a PFR came from, okay. So, this is in a brief nutshell recap of what you did for pretty much 2/3 of your undergrad CRE course, okay. It was a very quick recap. We are not going to reset our clock back and we are going to redo all of this all over again in the next 12 weeks. Okay. So, some of it might be boring for some of you guys, some of it might be exciting, but the whole idea is that we are going to look at the overall system more in its entirety. Okay. Some of it is going to be a recap, but or a relook at what you did in undergrad. Okay. Just hopefully with a different perspective. We can start a little bit with math concepts. Okay. What we are going to do is how to solve an ODE of this sort. Okay. And then what if the ODE was of this nature, what if the ODE was of this nature, and what if the ODE was of this nature. Okay. We will do that in the next lecture. What I am going to do today right now is just to give you an idea of what all situations we are going to encounter these equations. Okay. And then in the next lecture we are going to recap on the math concepts, and the lecture after that will be a tutorial where we will revise some of this math concepts, and then we will solve one more problem where you have reactions in series. Okay. So, any questions so far? Please interrupt me if you have any. Okay. So, in a batch reactor, let us say we have a reaction A going to B going to C. Okay. Let us say we were writing the balance for A. We are going to write this as okay. If this were a constant volume batch reactor, if this was constant volume and isothermal, we are going to get RA. Okay. Oh, or which is nothing but minus R1. Why? Because stoichiometric coefficient is -1. Okay. Let us say that R1 was first, let us say it was the first reaction was first order. We are going to get R1 is nothing but K1Ca. If this was power law, we are going to get R1 equal to K1Ca to the power alpha. If it was Michaelis-Menten type of kinetics, we are going to get this as if it was LHHW, to the power n. Okay. Okay. Where does Ka, Ca, Kb, Cb, Kc, Cc and so on comes from? We will come to that. When it comes to Michaelis-Menten equation, where do this form of equations come from? We will come to that later. Okay. But essentially this is what you are going to get for cases like this. Okay. So, if this was a first order reaction, you are going to get the equation in this form. Okay. K dCa by dt equal to minus Kca. So, your alpha is just minus K. Okay. If this was, if we look at this particular guy, and that is also a first order reaction, we are going to have an expression in this form. Okay, that is something that you will do in your tutorial. Next, not the next lecture, the lecture after that. Okay. If this was a power law model, you will get it in the form of dCA by dt equal to minus k Ca to the power alpha, where alpha is not equal to 1. That is when you are going to get this particular equation, and whether it is Michaelis-Menten or whether it is LHHW, you are going to get an equation of this form. Okay. Michaelis-Menten, it is K Ca divided by K plus Ca, or LHHW might be K Ca divided by 1 plus Ka Ca, and you will have it in this particular form. Okay. If it is 1 plus Ka Ca to the power 2, you can write it as 1 plus 2 Ka Ca plus Ka square Ca squared. It will be of, so beta naught plus beta 1 multiplied by Ca plus beta 2 multiplied by Ca squared. Okay. So, all of the things that we are going to do in math in the next lecture, okay, we are doing it because it is related to the most common rate expressions that you are going to see with respect to either a batch reactor or a PFR. Okay. How is it different in a PFR? PFR, you have steady state, this is 0, you will have equal to Rk, okay, and Rk might be Kca okay, and the same thing. You do not have to write this down, okay. This is just to give you an idea what we are going to do in the next class, why we are doing that, okay. So, as much as possible, please avoid missing the next class, which is tomorrow's class, okay. Any questions on what we have done so far? We are about half a lecture behind schedule, but that is fine. I am not going to rush to make up for lost time. We will make sure that we understand things. If you have any questions, please stop me and ask. We will go over concepts multiple times if needed. Alright then, we will see you in next class.